In this part of lesson 4, we're going to compute confidence intervals. And in this example, calendar sales at various Walton bookstores through time are displayed in the table at the bottom of this project. We are going to compute a 99% confidence interval for the number of calendars sold. If the degrees of freedom exceed 100, we're going to use a standard normal distribution, because for degrees of freedom over 100, the critical values from a t-distribution are getting really close to the critical values of a standard normal distribution. Now, confidence intervals are important because we cannot calculate the true population average. We cannot calculate the true standard deviation of a population. We cannot calculate the true proportion from a population. Candidates don't currently know what their support is among voters, so they have to sample a population. And when they sample the population, they get the sample proportion. Like, for example, a candidate might have 48% support amongst likely voters. If the margin of error is 4 percentage points, then at best, that candidate has 52% support, and at worst, 44% support. Same thing with firms. Firms have to estimate their customers' income. They don't know what their customers' income on average is because potential customers, because how many potential customers does a company have? Well, for an American company, they have potentially, 200 million people who could potentially buy their product. How would they calculate the average income of those 200 million people? They couldn't. So they have to do a random sample. And if that sample is random and representative, the sample mean is going to be really close to the population mean. Governments, for example, it cannot calculate the unemployment rate for a nation. It can calculate, though, an estimate of the unemployment rate for the nation. And that's what it does every month. It randomly samples the population of the United States to come up with an unemployment rate. Estimating these population parameters that we cannot know because we are not Greek gods is really important. And a confidence interval gives you kind of a worst case scenario and a best case scenario. Okay, so do this problem. We're going to copy the data. We're going to copy the word calendar sold all the way down to the word submit in this button, because this is an HTML table and we need to copy the stuff in the table and then something outside the table to preserve the table structure. I'm going to pick match destination formatting. I'm pasting that to a worksheet called L1 of a file that is named lesson underscore unit 4 underscore my last name. Now, before we move on, I'm going to grab all the cells that contain numbers that I just copied, not words, just the numbers. And then right here in this box here, I'm going to type QD for quantity demanded. You could also call it quantity sales, right? The company wants to know how many of these calendars to stock so that it can meet demand. And so the quantity that a company sells can be thought of as the quantity demanded by the consumer. And we want a best case and worst case scenario of that, right? So we're going to name that QD for quantity demanded. The next thing I want to do is I want to copy this table up here. Again, you copy everything inside the table and then something outside the table, right? So I'm going to grab the W there, copy. And again, I'm going to right click, match destination formatting. I'm going to delete the W. I'm going to widen this out. I'm going to rename the lower limit LL and the upper limit UL. To calculate the mean of the sample, equal average. And then I'm going to type Q. And notice when I type Q, I get QD, QS, And then I get some functions. So these are named cells. You can call these Excel objects. We named these. These down here are predefined functions in Excel. Some programmer built these for Excel. They lie underneath Excel. So we're going to type QD because we named this column of numbers quantity demanded, QD for short. So the average quantity demanded is 202.0537. I'm going to reduce the number of decimal places to 3 for all our answers because we want 3 decimal places. So to get the number in the sample, we need to type equal count A. Count A counts the number of cells in a range that are not empty. And then I'm going to type QD, and that counts everything in this blue box over here, right? And it looks like, how many do we have? It looks like we have a sample of 149. Now, because this is an integer, I'm going to reduce that to 149. Now, you might have noticed that you have a different sample mean, but you have the same number of stores. That's by design because you have a different random sample of 149 stores. And you might notice that maybe your average is really close to my average, but not exact. Again, that's by design because you have a different sample of 149 store sales. Correct? So what that means is if we replicate this experiment many times, each time we get a sample, a random sample of 149 stores, these numbers are going to be different, which means the mean is going to be different. That means the sample means vary, and they're going to vary around the population mean if the sampling is random and representative. So there's a distribution not only of calendars sold in my particular case, in your particular case, but there's another distribution here. The means are varying from student to student, right? Which means these sample means have a variance. My observations have a variance. Our means have a variance. The first variance we're going to calculate is the variance of your sample. So you need var.s. var.s is the variance of a sample. And again, I'm going to type QD for quantity demanded. The variance of my observations is 1,662.430 sold squared, right? This is squared. Every student's going to have a different variance of their observations. Every student's going to have a different average of their observations. So what that means is not only is there a distribution for the sample means, there's a distribution of variances. So there's two variances going on here. There's your variance of your sample, and there's the variances, right, that vary amongst us, the students and myself, right? Now, to estimate the variance of these sample means, these means vary from student to student. To estimate that variance, to estimate it, not calculate it, we're going to take the variance of your observations, in my case, 1,662.430. We're going to divide that by the sample size. This is an estimate, and all of us should have a number kind of close to 11.157. Your version of this number and my version of this number should be pretty close to each other because you're estimating the same thing. They're estimating the variance of these sample means, right? Everybody has different sample means, right? This is an estimate of the variance of those things. Imagine this experiment being conducted 1,000 times. We'll have 1,000 sets of those. We'll have 1,000 values here, and we'll have 1,000 values here, right? Within a given sample, the variance is quite large, right? You can see the variance is quite large, from 81 to probably around 300, right? There's a 300. So the variance is quite large. That's why this is really large. But everybody's probably going to have a mean pretty close to 200. Some might have 198 point something something. Others might have 201 point something something. Others might have 199 point something something. We're all going to have really close sample means, right? Because we have a really, really large sample, and the larger the sample gets, the closer these estimates are to truth. And that is why the variance of the means is much smaller than the variance of a given set of calendars sold. Now, this is calling for the standard error of the mean. Another name for the standard error of the mean is the standard deviation of sample means, which is plural, right? In order to convert a variance into a standard deviation, we have to take the square root of it. So what we're going to do here is we're going to type SQRT in front of that ratio. And that will give us the standard deviation of the sample means. That is also called the standard error of the mean. Confidence level is 99%. I'm going to type that right here. I'm going to type it as 99%, which ends up being 0.99. So I'm going to convert it to a percentage. The 99%, what does that mean? If I go down to the bottom here and I click on statdistributions.com and I click on two-sided mean to z, and then I type 0.99 here, you'll want to type whatever is here, right? Mine's 99%. You might have 95%. You might have 90%. Whatever's here, you want to type there. So I type 99%. So for any normal variable that has been standardized, and what do we mean by standardized? The mean has been subtracted off of it, and that difference has been divided by the standard deviation of the sample. That's a standardized variable, right? So any variable, any normal variable that's been standardized, the probability of being within 2.576 standard deviations of the mean is 0.99, right? And this is symmetric. So this number here is negative 2.576, right? So if this area here is 99%, that area there is half of 1%. And this white area here is half of 1%. Half of 1% plus half of 1% is 1%. And 1% plus 99% is 1. A confidence interval has two numbers. Any interval is going to have two numbers, the upper limit and the lower limit, right? Which means these two numbers are going to split this number line in three spots. We have the lower limit, we have the upper limit, we have area 1, area 2, and area 3, right? So two numbers on a number line split the area under distribution in three parts, right? 1, 2, and 3. Now, the area between the critical values, in my case, is 99%. The area outside of the shaded purple area, the white areas, together are 100% minus the 99%, right? Which will be 1%. Put that to a percentage. Now, because there are two areas outside of purple, this lower tail and that upper tail, we have to split this 1% into two. So I'm going to divide this by 2. And then I'll convert it to a percentage. So this is the area that is to the left of this critical value. Or it's the area that is to the right of this critical value, because we don't know the population variance. The actual distribution we want to use is the t-distribution. T dot inverse. We use T dot inverse because we're going to feed it an area under the curve, which is known as a probability. And then the degrees of freedom is a sample size minus 1. So the critical value is a negative 2.609. The problem, however, says if the degrees of freedom exceed 100, use a standard normal distribution. Now, why is that? Well, if I convert this to a t-distribution and I type 99% and my degrees of freedom R148, 149 minus 1, you can see that a normal distribution and a standard normal distribution, the numbers, the critical values are really close to each other. Historically, whenever the degrees of freedom have gotten over 100, people were just using the standard normal distribution because there's very little difference between the critical values of a standard normal and a normal when the degrees of freedom are high. So we're going to follow the instructions. We're going to use a standard normal distribution. So what I'm going to do here is I'm going to change this to, I'm going to get rid of the T. I'm going to type norm.s. That means standardized. And it only needs a probability value. And it's going to be pretty close to what we had before, 2.576. If we use the T distribution, 2.609. But if we use the standard normal distribution, it's 2.6 if we round to decimal place, right? So it's really close, T distribution value, right? So we go back here, we're going to click on normal distribution. We're going to click on two-sided mean. We're going to change this to 0.99. And we get 2.576 and negative 2.576. Put a negative in front of it. Two negatives make a positive, right? Now, the margin of error of a confidence interval is the critical value times the standard error of the mean. The lower limit of the confidence interval is the sample mean minus the margin of error. The upper limit of a confidence interval is the sample mean plus the margin of error. I'll pause the video and enter this information into our table here. All right, welcome back. With a confidence level, in my case, 99%, when you copy this in, do not include the percent symbol because outside the answer box already includes the word percent. So with a confidence level of 99%, the probability of population mean mu, a thing that we cannot know because we are not gods, being in the above confidence interval is either 0 or 1. We don't know what the population mean is. So we don't know if it's in the interval or it's outside the interval. So it's either 0 or 1, right? Because the population mean mu is just a fixed number that we cannot know. If we replicate this experiment 10,000 times, we're going to expect 10,000 unique sample means. We're going to expect 10,000 different sets of calendars sold. We're going to expect 10,000 different sample variances, 10,000 different standard errors of the mean. They're going to be pretty close to each other, though. So these are going to vary from sample to sample. We'll get 10,000 unique values of that, 10,000 unique values of that, 10,000 unique values of that, and 10,000 unique sets of those, right? We'll get 10,000 unique sets of these, which means we'll get 10,000 versions of that, right? These are going to be the same from sample to sample. We're going to replicate this thing 10,000 times. And if we do that, we expect 99% of the 10,000 resulting intervals, which is 9,900, 9,900 of them to contain this true population mean. I'm going to expect 50 of the resulting confidence intervals will be greater than the population mean. I'm going to expect 50 of these confidence intervals to be less than the population mean. And notice that this plus that equals 10,000. We are 99% confident that the population mean mu is in the above interval. This interval is our best and worst case scenario for our consumers' quantity demanded. At best, we're going to sell that. At worst, we're going to sell that quantity.